For what feels like forever, we've been promised this total game changer in battery technology, solid-state batteries. You know, the holy grail for electric cars. But they always seem to be just a few more years away.
And I mean, the promises are just incredible. Listen to this from Toyota. A 10-minute charge time and over 600 miles of range? Think about that. You could charge your car faster than you can grab a coffee and then drive for, what, 10 hours straight? It sounds like straight-up science fiction.
So what's the deal? Is the battery of the future finally here, or is it still just a bunch of hype? That's what we're going to unpack. We're going to dig into the real data, the expert analysis, and figure out what's what and when you might actually get to see one of these things in a car you can buy.
Okay, first things first. Let's dive into what solid state actually means, because, the term itself is a little more complicated than it sounds.
So at its very core, the big change here is the electrolyte. In all the lithium-ion batteries we use today, the ions have to move through this flammable liquid. A solid-state battery just gets rid of that liquid and replaces it with a super thin, stable slice of solid material. Could be a ceramic, a polymer, something like that.
And this visual really shows you what a fundamental shift that is. You're going from liquid to solid. And that one single change, well, it unlocks everything else. Suddenly, engineers can replace that clunky graphite anode with pure super energy-dense lithium metal. And the result? A battery that is, at least in theory, way safer, smaller, and a heck of a lot more powerful.
But, and this is a big but, here's the catch. Solid state has kind of become this catch-all term. Some of the batteries being tested are all solid state, which is the real prize, zero liquid. But a lot of them are semi or quasi-solid state, which means, yeah, they still have a tiny bit of liquid in there. There's no global standard, so it's often part of the whole marketing game.
But look, all that messy terminology hasn't stopped what is now a massive, high-stakes, global race to be the first one to crack mass production. So let's take a look at how that's all playing out.
And one of the biggest players really pushing the timeline is China. They've put a stake in the ground, targeting mass production by 2027. And that has absolutely lit a fire under everyone else, from legacy giants like Toyota in Japan to hot startups like QuantumScape over in the US.
Now, what's really fascinating here is just how detailed China's plan is. It's not just a vague promise, it's a 3-generation roadmap. Step 1, just get the basic tech working and make it last. Step 2, really crank up the energy density. And finally, Step 3, the grand prize. Hit 500 watt-hours per kilogram by using those pure lithium metal anodes. It's a very deliberate, state-driven push.
But, as we all know, having a plan and actually pulling it off are two very, very different things. For all the amazing progress happening in the lab, automakers and battery companies are now staring down this immense challenge of trying to scale it all up.
Yeah, this quote from an analysis by the P3 group just nails it. The journey from making a few perfect little cells in a pristine lab to churning out millions of them at a giant factory, it's famously difficult. It's a phase the industry literally calls production hell.
And the really crucial point here is that you can't just, flip a switch on a lithium-ion factory and start making solid-state batteries. The materials themselves are brand new and expensive. You need completely new machinery, and the physics are just harder. You have to press these solid layers together with incredible precision, sometimes under massive pressure. It's a monumental engineering headache.
And the deep science isn't totally solved either. These tiny, evil little spikes of lithium called dendrites, they can still grow and short out the battery. That solid electrolyte can develop tiny microcracks after hundreds of charges. And just getting ions to move as fast through a solid as they do through a liquid, that's still a fundamental hurdle they're trying to clear.
Now, with all this talk of complex, energy-intensive manufacturing, you would just assume these new batteries have to be worse for the environment to produce, right? Well, the data actually reveals a pretty surprising twist.
It's a totally logical question, right? If you need all new factories, new materials, and you're using high pressures and temperatures, that should mean a bigger carbon footprint. But that's not the whole story.
Look at this. According to a really detailed life cycle assessment, a solid-state battery can actually have a lower carbon footprint per kilowatt-hour than today's batteries. So why is that? It all comes down to one word, density. Because they pack so much more power into a much smaller space, you end up needing fewer raw materials and less energy overall to build a battery with the same capacity. Pretty cool.
So,
After looking at the tech, the global race, those insane production hurdles, and that surprising green twist, it's time for the verdict. Is this whole thing just hype, or is there real hope here?
This table, honestly, it tells the whole story. You look at every key performance metric: density, safety, charging speed, and solid state has this game-changing potential. But then you look at the metrics that matter right now: availability and cost, and conventional lithium-ion is still king, simply because the technology is mature and it's already scaled up.
And that all leads to the expert consensus. The progress is absolutely real. The prototypes are working, pilot plants are being built as we speak. But widespread commercialization, and by that I mean millions of affordable EVs with these batteries inside, that's still a long way off. Most analysts think we won't really see it hit the mainstream until the early 2030s.
So the revolution is coming, but it's not coming next year. The science works, but the engineering required to make it at scale is this final, massive mountain they still have to climb. The question really isn't if this technology will change everything, but rather, with today's batteries getting better and cheaper every single year, will the perfect battery arrive too late?